Hi, and welcome back. In the interpretation and reiteration phase of the life cycle assessment framework, we evaluate procedural and numerical steps. Evaluating the procedural steps tells us how complete and consistent our LCA is. Evaluating the numerical steps of our LCA tells us how robust our LCA is. Previously, we looked at procedural steps. Now let's look at the numerical steps. There's a range of numerical approaches you can use to evaluate your LCA. The numerical approaches are algorithms, which basically process the data included in your LCA in different ways in order to get an indication of how reliable your results are. Examples of such approaches include contribution analysis, perturbation analysis, that's the second one, uncertainty analysis, comparative analysis, and discernibility analysis. All 5 of these approaches can be applied to your inventory analysis, your characterization results, your normalization results, your weighted results, or the entire LCA. I will briefly explain the first 3 approaches in the list. Okay, so let's start with contribution analysis. Contribution analysis is also called dominance analysis. The basic idea is to identify the elements in your LCA which dominate. Contribution analysis shows us which emissions and resources contribute most to our impact assessment result. It can also tell us which unit process contributes most to our total emissions and resources used. If we are interested in the contribution of a specific unit process to an impact, contribution analysis will give us the answer. For example, if we go back to our bread bag product system example, contribution analysis can tell us what percentage of our fossil fuel resources consumed is due to crude oil extraction and what percentage is due to electricity use. We can also identify which unit process contributes most to global warming. When applying contribution analysis to unit processes, it is important to be aware that the contribution percentage of each unit process only reflects the elementary flows to and from the specific unit process and do not include the elementary flows to and from upstream processes. So for example, we may discover that the bread bag manufacturing unit process contributes very little to CO2 emissions. This is because the CO2 associated with the energy consumed are not reflected in the contribution results for this process. Instead, the CO2 emissions associated with the energy used in the manufacturing process will be reflected in the energy production unit process. The contribution analysis results are interesting in themselves because they can help us identify hotspots in the life of our product. We can also use contribution analysis to identify anomalies or unexpected results. Next, we have perturbation analysis, which allows us to identify the most sensitive and least sensitive input parameters in our LCA. If your LCA results are sensitive to changes to a specific input parameter, then it is important that those parameters are as precise as possible. For input parameters which have little influence on the results when they are adjusted, this precision is less important. Perturbation analysis can be useful for 2 reasons. 1, it tells us where in our model we need to be most sure of our data. It can also be used to draw conclusions about which unit processes in our product can be improved or optimized to achieve the largest gains in environmental performance. Perturbation analysis results are usually presented as a multiplier. The multiplier reflects the degree to which a certain change in input parameter propagates into a certain output result. Finally, we have uncertainty analysis, and you guessed it, it's about uncertainty. We can define uncertainty analysis as the systematic study of the propagation of input uncertainties into output uncertainties. In simple language, if you know the degree of certainty of each elementary flow recorded in our LCA, the certainty of characterization factors, the certainty of normalization factors, and the certainty of our weighting factors, then uncertainty analysis can determine the certainty of our final results. If we use LCA software, we include a probability distribution function for each input parameter. the software typically takes the probability density function for each input parameter and calculates different combinations of the various input values using Monte Carlo simulation. All the Monte Carlo simulations together give us a probability density function for each result. The results of, for example, CO2 emissions are presented along with the margin of uncertainty. Our product might emit 100 kilograms of CO2, and the uncertainty analysis will tell us what the standard deviation is either side of this value, for example, 10 kilograms of CO2. We therefore have a range in which our results occur and not just a single value. Just remember, in order to perform an uncertainty analysis, you need uncertainty data on the unit process level, and therefore the foreground data you need to collect yourself. Background databases usually include uncertainty data for each unit process. The procedural steps or your numerical steps allow you to identify parts of your LCA which can be improved in a further iteration. This brings us to the end of the knowledge video, and what a lot of knowledge you have already. See you next time.